So we have 8.4, which is angle measures and segment lengths, which is just allowing us to find even more parts of circles that we previously thought were just totally unable to be found. So as a warm-up, let's try to find angle 1. So in this picture, we definitely have an 80-degree angle here because these three have to add up to 180. And this has to be 100 then because 80 and 100 are supplementary. So the angle's 100. It also wants to know what this arc is here, AD, and also BC. And that's going to rely on the inscribed angles we've been studying. Notice how the 30 degree opens up to the blue, and the 30 is going to be half of that arc, so the arc must be double. Same thing here. We have 70 opening up to a yellow, so this has to be 140. And there's actually a relationship to link all of this together, and that's that the measure of angle 1 is 1/2 of 140 plus 60. So it's actually the average of the front arc and the back arc. And this is just an introduction, and there's no way you really could have came up with that maybe without studying this for a long time. But this is a fact, and this goes right here. And this will be our 1/2 front plus back theorem, which just says that if you want to find this angle where this point is anywhere in the circle, doesn't have to be the center, it could be anywhere, you have that it's equal to 1/2 of the front plus the back. Okay. And we have another theorem too, which is more about angles that are outside the circle. And it could be an angle formed by a secant and a secant and a tangent, or a tangent and a tangent. And a secant is a line passing through 2 points of a curve, or a circle in this case. So a secant is one of like these here, where it passes through 2 different locations. And the cool thing about this theorem, the far minus near, is that it doesn't matter if it's a tangent or secant. It's always the case that it is the measure of this angle here is half of far minus near. So it's really just these two that I'm going to be using for us for these next 4 questions. So for this guy, the angle's outside. It's opening up to a far minus a near. So this is like this picture here. So we're going to use that 20. This angle is half of the far minus near. So the far is 95. And Z is actually the near. So this is the far, and this is the near. Multiply both sides by 2. And then I would add Z to this side, and then subtract to get 55. Let's look at this one. So this one also opens up, and between these two, we see that we have a far and a near. So 70 is half of the far minus the near. And I'm just using this formula right here. So I'm going to double both sides and add 110. So we get 250 from that. Okay. For this one, the angle's inside. So we're looking at a front and a back. So the angle is 1/2 the front plus the back. It is the average of both of those arcs. So this ends up being 68 degrees in there. This angle right here is 68. And then also here we do have this angle. We have a front and we have a back. So 35 is 1/2 the front plus the back. Double both sides, and we get pretty quickly that x is 40. Okay, so those are some examples on how you can apply those theorems. And then, as kind of a recap, this is a really, really interesting picture we have here. So, angle 1, angle 2, and angle 3. We need to classify them and then also give what their measure should be. And angle 1 is a central angle, right? Because it's formed by the center and 2 points. All these angles are going to share these 2 points. So the central angle's measure is just equal to the arc. 2 is an inscribed angle. And we know from the last section, that an inscribed angle is half its arc. So this would be x over 2. And angle 3 is just the angle of 2 secants. So our formula for that would be that you would have a front arc x and a back arc, or I'm sorry, it would be a far arc minus a near arc. Because we're looking at this picture now, where this is going to be far, and this is near, and this is 3. So it's going to just be the formula 1/2 far minus near. So pretty interesting to link all of those together at once. And the last theorem, pretty much the last theorem of this whole unit, is one of the ones that's honestly probably the most surprising. And that's that no matter which diagram you have, it is always the case that AP times BP times CP times DP. I think I maybe said times. I meant equals in the middle. You know what I mean? It's right there. That formula is always true no matter which diagram you're dealing with. So we'll see that with the examples. We got plenty of examples. But we'll look at a proof 2 of this in our little GeoGebra book online. But it actually comes from, or at least for this one, it comes from the fact that these triangles are actually similar. Because these angles open up to the same arc, and so do these. So you get these similar triangles, and then we know that the sides are proportional on a similar triangle. So you could even set up a proportion, something like this, with proportional sides, and just really ends up getting this. I won't prove it, but we can use this setup no matter which arrangement we have. We just need to know that P is the intersection, and this part here, A and B have to always be on the same line, and C and D have to be on the same line as well. And sometimes I'll label it for you, and sometimes it won't be labeled for you. So let's start with this one here. So P is where these 2 lines cross. A, let's go here, and B goes here. So on this line, always has to be A and B. And then on this one, we have C and D. So I also sometimes flip it. So I want to be consistent and use the one that I like the most. And I'm going to reverse all the letters for no reason, but just because it's easier for me to say PA, PB, PC, PD than the other one. But it's the exact same thing. So all you do is you set up this master rule that we have, and you just plug in the lengths. So from P to A is 6. From P to B is actually 14. P to C is 7. And P to D is 7 plus Y. So this is going to be 84, 49 plus 7Y. This is 35. So Y is 5. It's a fairly friendly formula to use. You just got to make sure that you get this part right, that PD is the entire length. And when you have, so one of the cases is when you have a secant and a tangent. The tangent's interesting though, because this point actually now has 2 names. It's A and B. Imagine taking this line and dragging it up here slowly. So BA, 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 and eventually they're going to touch. So when I label this one, P is the intersection, I just label A and B as the same point. That's because the tangent only hits once. So A and B are kind of the same. We have C and D. So same formula. PA times PB is PC times PD. Oh, looks like I don't have much space there. So what does that mean for us? PA is 7, no, Z, and PB is also Z, and PC is 8, and PD is the entire length, which is 24. So we get 192 equals Z squared, and we would be forced to take a square root, and we're going to take the positive. So we get this, which is around 13.86. Okay, so same formula. And even when you have the other case where it's all inside the circle, these are called intersecting chords, you can still use the same formula. So P, and then pick a line. It has to have A and B on it. Pick a line. It has to have C and D on it. And that'll guarantee that our formula is going to work. PA, PB, PC, PD. So PA's, this one's a little easier. This is 3, PB is 7, PC is M, and PD is 6.5. So 21 equals 6.5 M, and we could just divide and get that M is around 3.23. Okay, so we can find lengths of intersecting chords with this theorem, and it's really strong. And then here's it's a repeat of this one up here where you have a tangent. So we're going to try and use their letters, just to have some flexibility. So D is like P. So it's going to be D to E, D to F, and then it's going to be this length, but G is actually 2 points in 1. So it'd be something like this. So this is going to be 7. DF is 7 plus Y, and these are both 10. So we're going to get 49 plus 7Y is 100. So 7Y is 51, and we get that Y is around 7.29. So just trying to play with the letters that we're given, but on the test they'll be labeled for you with P and A and B and C and D. Couple more. How would you set up this one? Well, we did one like it earlier. So this is the intersection. We'll pick a line to have A and B. We'll pick a line to have C and D. PA, PB, PC, PD. So P to A is 14. P to B is 34. P to C is 16, and P to D is actually 16 plus X. Okay, so pretty large numbers here. We'll go ahead and distribute the 16, subtract from both sides, and we're going to get 13.75 for X. Okay. And finally, another one that has everything on the inside, the intersecting chords theorem. P is that intersection between those chords. This one's got a little bit extra drawn in there. A is here, B, and then C and D have to be on the same line. You know, for example, if we swap these like this, the formula wouldn't work anymore. It would be all flipped around. It's like we set the proportion wrong. So remember, A and B have to be on the same line. And by line, I'm talking about these major intersections here. This one's kind of tricky because extra lines were drawn. But PA, PB is PC, PD. So X times 2X equals 8 times 9. And X times X is X squared, and then we have a 2 out front. We can divide by that 2. And eventually, 6 squared is 36. And we take negative 6 as well, but 6 is the only thing that would make sense for a distance. So anyhow, it's just 3 things. We have this new formula, we have this one here, and then we have this one here, which works for